Hi everybody, today we're going to talk about unconstrained nonlinear optimization. Okay, so in the previous lecture we talked about a constrained linear optimization, or in other words a linear program, satisfying this constraint. So now we don't have any constraint at all, we're just going to minimize or maximize the function of f of x, where x is a vector in Rn. So to give you a one-dimensional example, here we have a function like this, and we're trying to find probably this point, but we're going to have to also settle for points like these, which are local minimums. But we certainly know, for example, this is not a local minimum. I mean, this is basic calculus, but how do we know that? Because if we move in this direction, the value of it goes down. I mean, we can find the slope, the difference in whatever, so this is definitely not a local minimum. So let's look at some values that might help us understand whether a point is a minimum or not. And if we're able to answer that, then maybe we're able to find a good candidate for this optimization problem. So the gradient is a matrix, a column matrix of where we take the partial derivative of f with respect to each of the variables. So this is a function. All of these are like functions of f of x, but we can evaluate it at a point right here. Evaluate at a point x, and when we do so, if this thing is equal to 0, then we know that the slope, the sort of multivariable slope at the point is 0, and so that tells us a lot. It doesn't necessarily tell us that it's a local minimum, because there's examples like this where clearly the slope is 0 here, but it's actually opposite. It's a local maximum. It's not a local minimum. And there's also examples like this where it's neither a local maximum or a local minimum, but the slope right here is 0. Okay, so then in order to answer this question, we also, in some sense, we need to understand when it's a local minimum by understanding when the function is actually slowing up, like a bowl. So this is clearly a local minimum. So for that, we turn to the Hessian, which is a square matrix of this form. We're going to use like all these functions here, and then we're going to differentiate them once again with respect to another variable. So this will be dx1 d squared f. I'm going to use the notation here, dxn squared, and then on the values outside of this middle line, it's going to be linear combinations or combinations of the different variables, d squared f, dx2, dx1, and if f is nice enough, if f is whatever, continuous, differentiable, there's some constraint, then order of differentiation doesn't matter. Therefore, d squared f dx1 dx2 is d squared f dx2 dx1. So we're going to take the derivative in different order, which means that the Hessian is symmetric. So for example, the example given, it was like this, 2, 3, 3, 6, x1, for example. So you can see these two are the same value. If the Hessian, if the Hessian is positive definite, that means that this is a local minimum. Yeah, I guess, and gradient is 0, then this means it's a local minimum. So what does positive definite mean? This means that all the eigen values are positive, all of them. So again, what is an eigenvalue? An eigenvalue is a value where if you take a matrix A multiplied by this is an eigenvector x, then you end up with lambda x. So this would be it's a pair of possible. So this would be for this linear transformation A, lambda is a number which there exists a vector x, where when you take ax you get lambda x. So all it does is scale the so here's x and then here's lambda x. So lambda x and then x. Okay. So why, if all the eigenvalues are positive, why does this mean that it's a local minimum? So I guess the best way to visualize it is it's sort of like in the multi-dimensional case. So I guess a local minimum in general, it looks like intuition would be that it looks like a bowl, right? And that you found the point at the bottom where it's the local minimum. And so if the function is nice enough, you can probably so again, I forgot to mention that this Hessian is evaluated at a point x. And this is what I use here, this A. So if we have a bowl in the multi-dimensional case that we expect the local minimum to be, we can, if f is nice enough, then we can sort of do a Taylor expansion where we sort of basically the f is in a neighborhood around the point. The Hessian evaluated at x is going to be like it's not going to change too much. It's going to be close enough, to the so the difference in slope or whatever, the first derivative can be represented by the Hessian. And so if we, like, for example, take the so this would be the second derivative. I know this is like very sort of, I'm confusing notation and whatever. So if we take this, so the h will be like a tiny difference, and then x will be, so this is like a directional derivative, right? X will be our point that we're trying to evaluate, and h is a tiny difference. Then this change, given that the Hessian is positive semi-definite, this change is going to, basically it's going to be, it's going to like increase. So this is going to be bigger than this, right? Because this f so the Hessian is a linear transformation. So if applied to and it's always positive. So if we take in a neighbor, it's positive in the neighborhood around this, right? So if we take any slope around this, it's going to be bigger than the slope in the center, because in the neighborhood it's positive. Therefore, the function is going to slope upwards from the point. That's what I'm trying to say. Okay. So I think then in the video, he gives an example of this. So suppose we're trying to minimize this x squared 1 plus 3x1 x2 plus x squared 3. Then the gradient, so if we take so we're going to minimize, this is our function, and then we have, I guess we have two variables here, x1 and x2. So the gradient of this is going to be, well, here we take the derivative, it's going to be 2x1 plus 3x2, and here we have 3x2 squared plus, am I doing it right? Yes, plus 3x1, like this. And then we take the Hessian, so you can see this is a 2x1 matrix. This is a, yep. And then we take the Hessian, and then we differentiate twice with respect to x1, we get 2, then we differentiate this, 3, and then this would be, I think, 6x2. So you can see in this example, like I mentioned above, it is symmetric. If we evaluate this at 0, we get 2, 3, 3, 0, which, as it turns out, is not positive semi-definite. Therefore, this is, yeah, so at 0, if we, I mean, the gradient is 0, right? That's fine. But this Hessian actually is not positive definite. Therefore, it's not a local minimum. But the professor talks about a different point, which is negative 9/4 and 3/2. And this is definitely a local minimum. Okay, thank you so much. I'll see you next time.